Look at a classic question here. Thanks to Professor Strang for featuring this question in his calculus books over the years. A pentagon is formed by placing an isosceles triangle on a rectangle, as you see here in the diagram. If the perimeter of the pentagon is 10 inches, it could be 10, whatever you want it to be, but let's say 10 inches, find the lengths of the sides of the pentagon that will maximize the area of the pentagon. We're going to try to use Lagrange multipliers to solve this problem, a very classic topic in multivariable calculus. I added some bells and whistles to this diagram, so I'm going to call the horizontal base x and the vertical sides y and the sides of the isosceles triangle z. Now I'm going to drop a perpendicular, we'll call that h, and obviously this piece down here will be 1/2 of x. Okay, it kind of looks to me like the side of a barn. So it's like we're trying to maximize the area of this side of a barn that we're going to make. So using the Pythagorean theorem, clearly from up here, h squared plus x over 2 squared equals z squared. And by a little manipulation, that gives us h squared equals z squared minus x squared over 4. And I can isolate h. We're dealing with side lengths, distances that are positive, so we don't have to worry about plus or minus. We simply have h equals the square root of z squared minus x squared over 4. I want to clean that up a little bit more. I'm going to express the area of the pentagon in terms of 3 variables, a of x, y, and z. So clearly that would give us, first of all, x times y, the area of the rectangular base of this pentagon, plus the area of the triangular roof of the side of the barn, if you will. So that's going to be 1/2 x, or x over 2, times the height. And we already figured out the height to be square root of z squared minus x squared over 4. So we have this expression for the area of the pentagon in terms of 3 variables, x, y, and z. I'm going to just do a little simplification here in the radicand. I'm going to factor out a 1/4. And I will have x over 2 times the square root of 1/4 times 4z squared minus. Now, if I bring that 1/4 outside the radical, it becomes a 1/2. And you can see where I get the x over 4 from, right? I had x over 2 at first, but now I'm taking the square root of a 1/4 outside, so that's another 1/2 times x over 2, so now I have x over 4. But I still have an area function in terms of 3 variables, x, y, and z. What we're going to do with Lagrange multipliers, we're going to find the gradient, or del, of the function we want to optimize. In this case, we want to maximize the area. And we know that when we have a constrained optimization problem, that the gradients of the function that you wish to optimize and the gradient of the constraint equation are scalar multiples of one another. So we're going to use that technique to figure out the optimal or the maximum area of this side of the barn. So we're going to do, first of all, partial a with respect to x. Right? So you're going to do each piece with respect to x because we're trying to make del of the area function, del a. So partial a with respect to x, well, let's see. That's just going to give me y for the first piece, treating x as the variable. Y is like a constant, so y is what's left. Now with this other piece, I'm going to use the product rule. So I'm going to do first times the root of the second plus the second times the root of the first. So that's what you see here. First is x over 4 times the derivative of the second, which has a square root. Imagine a 1/2 exponent. So I have that power chain rule going on here. Right? So we have 1/2 4z squared minus x squared to the negative 1/2 times negative 2x plus, let's see, the second times the derivative of the first. Well, derivative of the first with respect to x, that's rather easy. That's just 1/4. So that's where I got this secondary piece. Cleaning that up a little bit, I have y equals, writing this first part of the product rule, as a fraction, and then rewriting this as a fraction. I see a least common denominator of 4 times the square root of z squared minus x squared, so I just need to multiply top and bottom by that square root that I see. So I now have this expression. Let's see if I can clean it up a little further. And looks like we have we have y, and we have 4z squared. We have a negative x squared here, 4z squared, another negative x squared. So we have 4z squared minus 2x squared over 4 times the square root of 4z squared minus x squared. And I think all we can do there is just reduce everything by a factor of 2. And so we have this expression for partial a with respect to x. Okay, so there's our partial a with respect to x expression. We still have 2 more pieces to create to make del a. Thankfully, the partial a with respect to y is very easy because we just treat x like a constant, so we just have x. Because last I checked, there's no y to be said, right? There's no y to be seen here in this piece, so that's like an entire constant. So we have that just goes to 0. There's your next piece of del a, and partial a with respect to z. Right? Okay, so now this x times y is like a constant, so that goes to 0. And all I have to do now is a little bit of product rule again with these 2 components, or these 2 pieces. So I have first times the root of the second plus the second. Thankfully, the root of the first is just a constant because we're partially differentiating with respect to z. So I'm left with simply xz over the square root of 4z squared minus x squared. And there's my last piece of del a. Oh my goodness. Del a is this vector in 3 space in terms of x, y, and z. Now we have to go to our constraint equation. Where do we get that from? Well, they told us that the perimeter of the Pentagon is 10 inches. The perimeter of the Pentagon is 10 inches. So what is the perimeter of that Pentagon? Well, if you recall, we had a bottom piece x, right? We had 2 side pieces, 2 y's, and we had 2 pieces of the roof of the barn, 2z, and that adds up to 10. Okay? So if we express the constraint equation as a level surface, right, we'll find that we can name it g of x, y, z, moving everything over to one side, equals x plus 2y plus 2z minus 10 equals 0. There's our level surface, often called a level curve as well. So thankfully, finding del g is a lot simpler. Del g is simply partial derivative with respect to x, y, and z of this side of the equation. You just get the vector 1, 2, 2. But now the method of Lagrange multipliers is to use this equation that del a is a scalar multiple of del g. And that's going to lead us to finding the maximum we seek. So let's do that. So we have each piece of del a equal to lambda times 1, 2, 2. That means y plus 2z squared minus x squared is 2 over 2 square root of 4z squared minus x squared must equal lambda times 1, or just lambda. X must equal 2 times lambda. And xz over the square root of 4z squared minus x squared would equal, again, 2 times lambda. Right? So we have these 3 equations, and the trick with Lagrange multiplier problems is how to manipulate those equations so it finally reveals what the maximum will be. So starting here, well, there's one obvious conclusion we can make. If x equals 2 lambda, clearly lambda equals x over 2, that's for sure. That's going to come in handy later. What else can we conclude? Well, we also have 2 lambda equal to 2 different things here. You have 2 lambda equal x, you have 2 lambda equal xz over the square root of z, 4z squared minus x squared. Now remember, x does not equal 0. X is a positive side length of a barn, if you will, or a pentagon. So the fact that we have this equation, we're entitled to divide by x because x does not equal 0. So now we have this expression with z, x, and x squared and z squared. So we have this expression here. Let's see if we can simplify it a little bit. We'll cross multiplication. You get z equals the square root of 4z squared minus x squared. Squaring both sides, you get z squared equals 4z squared minus x squared. And what else we have? Well, we have some like terms here. So we could simplify into x squared equals 3z squared, or x equals z root 3. Now that's pretty useful. Now we have x in terms of z. So let's go back to our constraint equation. X plus 2y plus 2z equals 10. I'm trying to simplify my life here. We now know that x equals z root 3. Well, I'm going to substitute x with z root 3. Now I have an equation in terms of just y and z. And if we look again at the other piece, let's see, there was another piece of del A, right? This piece of del A, and that's supposed to equal lambda, okay? So looking at that, we have y equals y plus this fraction, right? That's part of del A equals lambda. But wait a second, we said lambda equals x over 2. So we're going to put that x over 2 in there. And you'll notice something else we did rather sneakily. It said 2z minus x squared. But wait a second, x squared, remember, is 3z squared. So you see how I snuck that in there? I replaced that minus x squared with minus 3z squared. And not just there, I also did it here. Here we have 4z squared minus x squared, but that's really the same as 4z squared minus 3z squared. Again, because x squared equals 3z squared. Comes in handy, right? So once you simplify all that, you see it simplifies greatly. This becomes, let's see, y minus, this is minus z squared up top. Here's just 2 times, oh, here's another thing, 2 times the square root of just z squared. And since we're dealing with positive values here, because it's a geometry problem, the square root of z squared is just z. So I have y minus z squared over 2z equals x over 2, which of course can be further simplified to y minus z over 2 equals x over 2. Moving everything over, y equals x over 2 plus z over 2. But wait a minute, I know that x equals z root 3. So we have y equals z root 3 over 2 plus z over 2. Okay? Another way to write that, factoring out the z, y equals z times 1 plus root 3 over 2. All right, we're getting there. I promise, we're getting there. Now we have, back to our constraint equation, we now have y in terms of z. If I substitute that y there in terms of z, well, I'll have everything in terms of z. I can solve for z. Okay? So that's exactly what I'm going to do. So 2 times y becomes 2 times this expression. Clearly the 2's will cancel. I'm just left with z times 1 plus root 3. And then finally, I can solve for z, right? Dividing 10 by all this radical stuff, which can be simplified a little bit. And you'll get z equals 20 root 3 minus 30 over 3. We finally know the sides of the top part of the pentagon, the roof of the barn, if you will. We know all those sides. But wait a minute, we also know that y equals z times 1 plus root 3 over 2. So I take the z value we just found, multiply it by 1 plus root 3 over 2, and we have our y value. Now we know how tall the walls of the side walls of the barn will be. And the only thing left is to figure out what x is. But remember, in the previous slide, we had x equals z root 3. So now we take our z value, and finally we multiply it by root 3, and we get 20 minus 10 root 3. Those are the side lengths that will optimize or maximize the area of this pentagon. And while we're at it, we could also figure out lambda, right? If you want to figure out the scalar multiple involved in the Lagrange multipliers, lambda equaled x over 2. So all you got to do is take your x value and divide it by 2, and you get your lambda. By the way, this is, as I mentioned, is a classic problem. You could generalize it given any perimeter. And if you took the time to just let P stand for that perimeter and go along for the ride, you'll get these expressions that will result in whatever answer you need for whatever perimeter is given to you. In fact, if you take P equals 10, which is what we had in this problem, you will get the very answers that we just computed. Right? These radicals for x, y, and z. Now, students often look at this question and say, you know what, I would have never thought of all those details. That's a lot. There are other approaches to solving this problem. So there's your answer. But if you want some other approaches, let's take a look. Let's go back to that diagram we had. You'll notice that we have little angles theta here, which are often not talked about. But you could approach the problem looking at it that way for a second. Cosine theta obviously would be adjacent over hypotenuse. So that's x over 2 over z, which allows us to solve for z in terms of x and theta. So here I have z equals x over 2 secant theta. Also, tan theta equals opposite over adjacent, or h over x over 2. That allows me to solve for h in terms of x and theta. So where am I going with this? Well, again, if you go to your constraint equation, right, and you replace z with x over 2 secant theta, we now have an expression in terms of x, y, and theta for our constraint equation. And we'll have 2y plus x times secant theta plus 1, right? If I factor out the x from those two terms, I have an x term here, an x term here. If I factor out an x, I can express the modified constraint equation this way. And that allows me to isolate y in terms of x and theta. So right now, I could also use my h equals x over 2 tan theta and get the area function that I want to optimize in terms of x, y, and theta. So that would be x times y plus 1/2 base, or 1/2 x times the height. All I did is replace the height with x over 2 tan theta. And I could write that as xy plus, looks like x squared over 4 tan theta. Okay? So now I have my constraint equation. I have my area equation. Let's see if we could use that y expression. Y is expressed in terms of x and theta in my area function. I'm going to replace the y that you see here with this expression in terms of x and theta. And I've changed my area function. My area function was in terms of 3 variables, x, y, and theta, but now I've changed it into something with just 2 variables. Area of, in terms of theta and x. If I clean it up a little bit, right, it'll look like this. Okay. Now here's where we still want to use multivariable calculus, but you have to embrace some conceptual understanding here. We know we can maximize this area. That's what the question's asking us, right? So there must be some value of x that's going to be part of this solution. So imagine we knew what that x was. We want to hold it fixed at that value. Let's treat x as a constant value. And now we'll differentiate this multivariable function in terms of theta and x. We're going to differentiate partially with respect to theta, treating x as a constant, because we know x has to be some length that will make this problem work out. But what happens? What happens when you differentiate a of theta x? If you partially differentiate with respect to theta, okay, 5x, that's just a constant, that's gone. And really, if I differentiate with respect to theta, even negative x squared over 2 is a constant, so I just got to multiply that negative x squared over 2 times the derivative secant theta, which is secant theta tan theta, plus, again, x squared over 4 is like a constant, derivative tan theta is secant squared theta. Now again, x is a non-zero value, so I can cancel it out on both sides and multiply both sides by 4. Oh my goodness, I have an equation just in terms of theta. And I want to know when it's going to be a maximum. So I want to set this derivative equal to 0. And if I do that with a little trigonometric manipulation, we can actually figure out what the angle is. The angle that's going to maximize this area of this pentagon is going to be 30 degrees, or pi over 6 radians. Now that I know the angle, this problem becomes greatly simplified. So I used to have an area function in terms of 3 variables, but I figured out that theta was pi over 6. Now I know that tan theta is 1 over root 3. So now I can make an area function in terms of x and y. Instead of saying xy plus x squared over 4 times tan theta, I could say xy plus x squared over 4 root 3 by simply substituting the tangent of theta, which I know. I know the tangent of pi over 6 is 1 over root 3. Furthermore, I know that z equals x over 2 secant theta, and I know what theta is again, so I can figure out z in terms of x. Z equals x over root 3. So my constraint equation can also be simplified into a function of just 2 variables by substituting z with x over root 3. So that's where I get 2 times z has now become 2x over root 3. And using our Lagrange multiplier techniques once again, all I have is that del A, this time A in terms of 2 variables, would equal lambda del G. So del A is a lot easier to find this time. Del A is just y plus x over 2 root 3 comma x, taking the partial derivatives with respect to x and y of this piece. And del G is simple as well. using this function, I get 1 plus 2 over root 3 comma 2. Now we're going to substitute, right? Remember from before and also here that x equals 2 lambda. So lambda equals x over 2. And we're going to substitute. Right? So we're going to equate y plus x over 2 root 3 equals lambda times 1 plus 2 over root 3. But I'm going to substitute that lambda with x over 2. So instead of saying lambda times 1 plus 2 over root 3, I'm going to say x over 2 times 1 plus 2 over root 3. And once we do that, we're kind of almost done, because we could then simplify and get y in terms of x. So I take that expression for y in terms of x, maybe clean it up a little bit, factor things, get some radicals together, and now I go back to my constraint equation. I now know y in terms of x. So I substitute this y with this expression in terms of x, put it right here, and I have, here we go again, I have the ability to solve for x. X would be 10 divided by 2 plus root 3 after some simplification, and that becomes our familiar answer, 20 minus 10 root 3. And then I go back to my y equation, multiply that x value times this radical expression, get the same answer for y, 15 minus 5 root 3 over 3. And lastly, we knew that z equals x over root 3, and we get our familiar answer of 20 root 3 minus 30 over 3. Hey, if you want lambda as well, you can still get that too. Simply divide x by 2. So students sometimes find this a little more accessible because you're using Lagrange multiplier techniques with functions of 2 variables instead of 3. But is there yet another way to do this problem, even for a single variable calculus student? Well, sure. Let's go back to that equation real quick. Here we have a function for area in terms of 2 variables, but we know what our angle is. So we know what secant pi over 6 is, and we have our modified constraint equation here. That leads to some interesting results as well, right? We have x plus 2y plus 2x over root 3 for the secant theta, right? And factoring out the x, moving things around, we could solve for y in terms of x. Okay? We could solve for y in terms of x. And once I solve for y in terms of x, I can go to my area function, and I could substitute this, as messy as it may look. I can substitute it here, and I can get an area function in terms of a single variable x, right? Here's what it looks like. And then you can just use your single variable calculus techniques. Take the derivative, a prime, set it equal to 0, solve for x, and oh my goodness, lo and behold, it's the same value. And once you get that x value, you plug it into your y equation, which was expressed in terms of x. Here it is, and you get the same y value. And then you know the routine by now. You go to z equals x over 2 secant theta, but you know what secant theta is, and there you get your z value. And I think you know how to get lambda by now. So again, we've approached this from Lagrange multipliers with functions of 3 variables, then 2 variables, and then finally, we relegated it to a single variable problem. So single variable calculus teachers might want to present this in their single variable calculus classes and remind students that we could revisit it from a multivariable perspective in 2 ways once you get to multivariable calculus. So I really hope you enjoyed this video. Thanks for staying for all 3 methods if you did. The first 10 minutes of the video just dealt with the classic method that many textbooks present as a solution but don't give many details to. So I hope you found video helpful. Please like and subscribe, and we'll see you next video, everyone.